Good morning, everyone. Welcome back to class. Hope you had a great week off. A quick announcement, I just sent an email to the class and scheduled the Carmen Zoom meetings for today. So today's office hour, my 2 to 3 office hour will be on Zoom instead of in person. Same thing on Friday. Unfortunately, my kids are on spring break this week. Be nice if they lined up. But Wednesday's office hour will be right after class, kind of as usual. If you do have questions like right after class, maybe more questions after class if you want to try to get them answered, just feel free to come up after class and we'll try to take care of those. But we want to get back into Lewis structures and kind of go back through these rules. When I was taking a look at these rules, I kind of think I accidentally had hit enter. So I uploaded this slide. It's in the lecture slide page. So one of the bullet points didn't quite look right. So I did re-upload these slides. But let's talk about diatomic molecules first, because these rules here, before we get back into them, are for like 3+ atoms. If we're looking at a molecule like N2 or carbon monoxide, the thing that we're going to do for these structures is we're going to try to satisfy the octet rule for all atoms if we can do so. And for the most part we can. We'll see at the very end of the notes, we'll see a case of an odd electron count, how we handle those towards the end of the notes for a diatomic molecule. But for this, I'm just looking at 10 total electrons to distribute. I'm counting the valence electrons, so nitrogen has 5 valence electrons each. So that's where I get 10 from. So I have 10 electrons to distribute. And so the only way I can satisfy 8 electrons near each atom, where for the octet rule, we would count all the electrons surrounding the atom. And so that gives me 8 for each of the nitrogen atoms. And so that's how we can kind of see each nitrogen has 8 electrons nearest to it, satisfying the octet rule. If I do this for carbon monoxide, carbon would have 4 valence electrons, oxygen 6. So again, I just want to try to satisfy the octet rule for 10 electrons with that same type of Lewis structure. So I end up with this Lewis structure here. And then we might take account of formal charge. Formal charge is really, and the book puts an equation to it, but to me it's really as simple as saying for the nitrogen atom, what would the charge of that atom be? If I had nitrogen with 5 electrons, that atom would be neutral in charge. If I had the other, so if I break the bonding pair electrons in half, I have 5 electrons nearest each of the nitrogens. So formal charge rule, or the idea of calculating formal charges, is just break the bonds in half and then take note of where the electrons are. But then if you think of octet rule, you're thinking all of the electrons in the bond kind of count towards the octet rule. So we don't end up with 8 electrons around each end at the same time, on average just 5, but then they have the valence of all 8. So they're getting the valence picture of all 8 here. And so we break the bonds in half, calculate the charge. Each nitrogen's neutral in charge, which is good because if I add up the formal charges, they should add up to the charge of the molecule. So if one n is 0, the other should be 0. So 0 plus 0 is 0 for overall charge neutral. Now carbon monoxide, same Lewis structure, but different charges emerge because carbon should only have 4 valence electrons. So the charge of a carbon atom with 5 electrons, so what would the charge be if carbon had 5 electrons in its valence? It would be -1, because carbon's picked up 1 extra electron. Carbon should have 4 electrons for neutral charge. It has 5 here, so that's how we get -1. And then oxygen should have 6, only has 5, and that's +1. So I have -1 for carbon, +1 for oxygen. Those sum up to 0 for overall charge neutral. So I get charge neutral, -1 +1 equal to 0. So for diatomic molecules, I'm just trying to satisfy the octet rule as my guidepost for my Lewis structure. I'm just kind of counting electrons. And the idea would be 10 electrons goes triple bond, 12 would go double, 12's like O2. If I had 14 electrons available, that would be something like F2 or Cl2. I'd have enough electrons to go with a single bond. Or if we have hydrogen involved, hydrogen only needs 2, so maybe we have a molecule like HF or HCl, where chlorine has 7 valence electrons, hydrogen has 1, so we pair up and make this single bond. So if I have 8 electrons involving hydrogen, hydrogen gets its 2, chlorine gets its 8, we share the electron, each atom ends up overall neutral in charge. Then we come back to the reminder of polarity, and bonds can be polarized if the atoms have a difference in electronegativity. So just kind of summarizing some of the things we went through before break, chlorine is more electronegative, so our right side elements, fluorine's the most electronegative, NO and F are the 3 most electronegative, chlorine's in that same ballpark. So those atoms are going to pull the bonding pair electrons closer towards that more electronegative atom, and it's going to pick up a partial negative and a partial positive. And so you can kind of think how the bond, once you kind of predict or calculate your formal charges, think about how the bonding pair electrons are going to slant towards the more electronegative atom. It does this in CO. This is a problem that you can see on a recitation activity. Oxygen is still more electronegative. It's going to try to pull the triple bond electrons closer towards the O, but carbon still remains as the negative atom. The recitation activity, I'll give you a dipole moment. I think it's not entirely a good use of lecture time to go through that problem again, but with a dipole moment and a bond length, you can calculate charges. On the recitation activity, you can calculate the charge on carbon. Turns out it's relatively small. It's not quite -1, but it's still negative, and it's still really important. Carbon monoxide, to me, is one of the most important molecules to understand and to really be afraid of because it is toxic. Okay, so let's get back into the Lewis structure rules. Let's examine these for our triatomic and larger molecules. So here we want to go through that process still summing up our valence electrons. Identifying the central atom is usually pretty easy in this chapter because it's usually the most obvious. It would be like SO4 2-, so sulfur is the central atom. It's usually the first atom, or it's the thing the others are kind of clearly attached to. So it's sometimes the book says it's usually the less electronegative atom, but I mean it's usually pretty obvious. Like when we say something like PCl3, it's pretty obvious. Phosphorus has the 3 chlorines attached to it. So it's usually not too hard to identify the central atom. We attach the atoms to the central atom with a single bond. So start with single bonds. Complete the octets of the non-central atoms. So don't necessarily complete the octet of the central atom. And then place any unassigned electrons. If we have electrons that haven't been assigned, then those go on to the central atom, even if it requires the central atom to expand its octet. So we've seen some examples of that, and we'll see some more as we continue. And then if we don't have enough electrons to give that non-central atom its octet, we can then consider multiple bonds. So we might think, can we make a double bond or multiple double bonds? What we want to do is we want to reduce the magnitudes of formal charge. The octet rule would say we can't expand an octet past 8 electrons. That's the octet rule. There's a supposed or a way of thinking of a formal charge rule of minimizing magnitudes of formal charge. So the formal charge rule would say that we may be allowed to expand an octet if it leads to lower magnitudes of formal charge, as long as the central atoms in the 3rd row are higher in the periodic table. And we'll see some examples of this as we continue, but the idea will be 2nd row atoms, like say nitrogen. Nitrogen cannot expand its octet. Nitrogen can have a maximum of 8 electrons. It can't have 10. We'll see a consequence and example of that once we get through a couple examples. So we were finishing on this slide on Friday. If you remember, for water, the idea would be 2 times 1 plus 6 for 8 electrons, just to kind of show the basic idea of the rule. The 2 hydrogens attached to O. See, O is not the more electronegative here. That's why I don't really think the book should stress that rule, because you would think hydrogen's less electronegative and should be the central atom. Hydrogen's never the central atom. Hydrogen's always on the outside because it can only form 1 bond. So we have our hydrogen atom single bonded to water. Don't worry about geometry in this chapter. We'll worry about geometry of what this molecule looks like in the next chapter. And so if I count my electrons, that's 4. So I have 4 electrons left to go. Those go onto the central atom. And so that's the basic idea of the rule or the way of coming up with the water Lewis structure. Of course, we had come up with it before by just kind of picturing water with this Lewis structure, hydrogen with this Lewis structure, and pairing up. In some cases, this works easily. Some cases, it's a little tricky to get the Lewis structure, the dot diagram structure to work out. So a lot of times I go back to the rules if I'm not entirely sure of the Lewis structure. You may also just have known that that was a Lewis structure of water. It's not necessarily wrong. If I ask you for like a Lewis structure on a quiz, or there's no quizzes, but like on a homework assignment or on a lab exam question, if you're asked for a Lewis structure, you just know what it is, that's fine. You can memorize these, but you don't really have to memorize them. It's just a matter of trying to follow the rules. OF2, oxygen has 6 valence electrons, just using the periodic table. 2 times 7 for the fluorines. That gives us a total of 20 electrons, so central oxygen, fluorines attached. Complete the octets of the non-central atoms, meaning put electron pairs around the non-central atoms first. don't yet consider filling the octet with electrons on the central atom until we count. When I count electrons, I have 8 here, I have 8 here, so that's 16 electrons distributed. I have 4 electrons to go, so I put them onto the central atom. So that's the basic idea of like unassigned electrons placed onto the central atom. Now for PF5, presumably I'm going to expand the octet here. If I think of the octet role, I have to single bond everything to that central atom. So I'm going to start with phosphorus. I'm going to have 5 fluorines attached. Again, I'm not thinking about the geometry of what this thing really looks like. I'm just trying to get the Lewis structure to tell me how many bonds are there. Are they single or double bonds or triple bonds? How many of them are there? Where are the lone pairs? Let's calculate some formal charges. I kind of haven't done that in the last 2 examples. Maybe we'll go back after we finish PF5 and think about some formal charges. But it's not always going to be the case that formal charges are 0, but it's pretty common that they'll be 0. We'll see it a lot, that in a stable molecule, it's not going to be uncommon to find, like in PF5, that the formal charges are all 0 here. So at this point, the formal charges of the fluorine should have 7 electrons closest to it, and it does. So just break one of the bonds in half, or break all the bonds in half, and think about the charges of these atoms. Think about how many electrons there are on each atom. So phosphorus would have 5 electrons closest to it, and it should have 5. Phosphorus with 5 electrons is neutral, and I subtract the 5 that are closest to it. And so this is just my valence count from the periodic table. It's like how many valence electrons gives an atom a neutral charge, and then how many electrons are there closest to the structure. So the number I subtract is examining the Lewis structure, count of electrons. So the idea is phosphorus should have 5. If it has 5, it's neutral, and it has 5, hence it's neutral. If we had more electrons, it would be negative. If I had fewer electrons than 5, it would be positive. So phosphorus is 0. The fluorines are all 0. Fluorine should have 7, and they have 7. And again, the formal charges should all sum up to the charge in the molecule. The molecule's neutral, so all the zeros add up to 0. That's good. That's what they should add up to. If I go back through water, of course, hydrogen should have 1 electron, and it does, so that's neutral. And the oxygen should be neutral as well. Should have 6 electrons closest to it, and it does. And so that's a 0 charged oxygen. Now, where's the actual buildup of charge in water? Like, which atoms have the positive versus negative charge when we think about bond polarity? So the OH bond is certainly going to be polar because oxygen's more electronegative. The electrons are going to slant towards the O, putting more electrons closer to O. What does that do to its charge? Makes it become negative. So we end up with the partial negative on water, and then the partial positive charges on the hydrogen atoms. And this is important. This is how water actually dissolves ionic compounds. This is how sodium chloride, if you remember, we started with a picture of the sodium plus charge as being surrounded by the O atom of water because that's what carries the negative charge in O. So you get that plus minus electrostatic force of attraction. And then the chloride ion, so sodium chloride dissolves in water, also because the chloride ion is surrounded by the hydrogen in water because you get that positive negative interaction. So you might remember how the negative charge can help surround something like sodium plus and then chlorine minus to break apart that solid ionic compound. OF2, which atom's negative, which one's positive in OF2? Just think about which atom's more electronegative. Is O more electronegative or is F? It's fluorine. Fluorine's the most electronegative element. So fluorine has the greatest desire for electrons, so it makes fluorine be the negative atom here, and then oxygen goes positive. And if you recall, from chapter 4, when we were assigning oxidation numbers, the oxidation number of fluorine would have been -1, and then the oxidation number of oxygen would have been +2. So if you remember oxidation number rules for like OF2, if you remember this negative and +2 process that we came up with for our oxidation numbers, that these were to help us kind of predict the signs of these partial charges. So the charges aren't fully -1 and +2. It's not really an ionic compound, but the charges on the F are negative because F has the stronger pull for the electrons in the bond pair, and oxygen has a less pull for those electrons. So it's all about, think about how oxygen's a little bit bigger than fluorine in terms of atomic size from chapter 7. Fluorine's smaller, has a higher charge, so that's what's helping pull the electrons closer towards the fluorine, is that small size and relatively high effective nuclear charge, higher than O. And so fluorine stays negative here. So fluorine's always going to be negative in compounds. It's never going to go positive because it has such a strong pull for electrons. What about ClF3? Kind of wedged over here. Let's put in this area here. So ClF3, again, I just want to start with my chlorine, attach my fluorine atoms, give the fluorines their octet. I could have or should have started with the count of electrons as well. So chlorine has 7, fluorine, each of them has 7, so that's 28 total valence electrons to distribute. And so far I've distributed 24 electrons. So that leaves 4 electrons unassigned, so I put those onto the chlorine atom. Again, no thought of geometry, I'm just like attaching those to chlorine, so when I think of chlorine's charge, those lone pairs are fully on chlorine, and then half of each of the bonding pairs. And then, maybe not the most common compound, ClF3, but all the atoms are neutral in charge. So the fluorines are neutral in formal charge. The chlorine is also neutral in formal charge. Chlorine should have 7 electrons closest to it, and it has 1, 2, 3, 4, 5, 6, 7 closest to it. So our formal charge here for chlorine is also neutral at 0. Now, which atom's actually negative charge in the compound, though? It's going to be the fluorine. So fluorine's going to pull electrons back off of the chlorine atom. And these compounds, like if you look at chlorine, chlorine has an expanded octet. So chlorine's octet, we say, is expanded because if you consider all these electrons here, we'd have 10 electrons closest to chlorine, not 8. So we've expanded that octet past 8 electrons. So the Lewis structure shows what we call an octet rule violation, but that's okay. There's no other way to sketch the Lewis structure. And now if you think about it, the best place to put those extra electrons are on chlorine because fluorine's going to pull the bond pair electrons off of chlorine. So like what the chlorines or the fluorine atoms are going to do, they're going to make room for those extra electrons by pulling the bonding pair electrons off the chlorine atom. So these compounds that have expanded octets will almost always do so with a really electronegative atom on the outside of the atom pulling those electrons back off an atom. I think we already had looked at SF6 before, but there's a compound SF6, 6 plus 7 times 6, so that's 42 plus 6, that's 48 electrons. Relatively simple Lewis structure in the case of having all 6 of those fluorines attached to the sulfur. I think I even mentioned how you can breathe this in, and I've done that before. I really don't like doing it because this compound, it's a fun demo to do. I've done it like twice, and when you breathe the gas in, you can feel the fumes of it coming out. It makes your voice go real deep instead of high like helium does. So it changes the pitch of your voice, you sound funny, and you literally feel this like odor coming out of your mouth that makes you think you're probably gonna die if you do this too many times. So I don't know if it's entirely a safe demo to do, so I don't like doing it. But you end up with the structure here of SF6 where sulfur has 12 total electrons surrounding it in the Lewis structure, which seems really bad, right? But the molecule exists, it's stable enough to allegedly breathe in. It's inert, it doesn't really react with anything either, which is kind of interesting that it's so unreactive even though it has all these extra electrons on sulfur. Well, one observation would be that all the atoms are neutral in formal charge, so that's relatively good, I guess. But then the other thing is, like, how can we pack 12 electrons around that sulfur atom? Well, the fluorines are just pulling the electrons back off. So the fluorines are designed, the compound has the design of the fluorines pulling those electrons away from sulfur to create the space for those electrons around the central atom. Now, let's push it another step forward. OF6, we see a lot of things are periodic. What about OF6? Can we bottle and breathe in OF6? No, you can't do that because it's not a stable molecule like SF6 is. Why? Well, oxygen's smaller, and now I gotta fit all those negative atoms really close together and they repel each other. So what's good about sulfur is it's bigger, puts the fluorines further away, and then as it sort of pulling the electrons off sulfur, it's lengthening those bonds, putting the fluorines even further away. So the molecule kind of has this design that the fluorines are so far away from each other that they don't really get to experience the repulsion that they would have if that central atom were smaller. And so if you go back to like the rule of the Lewis structure, you want the central atom to expand an octet to be in the third row because that's what gives you a big enough size to accommodate all that charge being centered around a central atom. Okay, so one regard, we just really want you to be able to sketch Lewis structures. It's nice if we understand why some of the rules are the way they are, and then how the rules are trying to describe like what compounds actually exist so that we can get a picture of what some of these things kind of look like. Okay, so let's talk about Lewis structures that have some built-in charges, like NH4 plus is ammonium cation. We know that's an important cation, we know it exists. How do we come up with its Lewis structure? Well, the valence count would start just by thinking nitrogen should have 5 valence electrons, 1 times 4 for the hydrogens. And then what do we do for the charge? We have to subtract an electron. We take an electron away is how we get net positive. If I add an electron, that would be NH4 minus. So I have to take an electron away to get the positive charge. So think about how the charge of NH4 here is positive relative to the number of electrons that those atoms have. So if nitrogen had 5, if the hydrogens had all 4, if I had 9 total electrons, that would be NH4 neutral. To get to NH4 plus, I have to take an electron away. So cations, we take an electron away. This is because of the positive charge. If we had a +2, I'd take 2 electrons away. If I had a +3, I'd take 3 electrons away. This is the same thought of like Al3 plus is the charge of aluminum, 13 electrons minus 3 to get to 10. Same basic thought of taking electrons away to get a cation, take electrons away from NH4 plus to get the cations count. So I have a total of 8 electrons for the ammonium cation. So I start with my central nitrogen, single bond, the non-central atoms. And then that's essentially it other than calculating charges. And so the formal charges of these atoms, if I break the bonding pairs in half, of course the hydrogens are all 0, but then what's the nitrogen atom's charge? So nitrogen only has 4 electrons surrounding it, and therefore has to go positive. So it becomes +1 in formal charge. So we've got +1 for N, 0s for all the hydrogens. Now, nitrogen does end up with the positive charge, but do you think it's really +1 in a real molecule? Probably not, because nitrogen's more electronegative. It's going to try to pull these electron pairs in towards itself to sort of make up for that charge. So its real charge is probably going to be some kind of partial charge, still positive, probably not quite +1, and then the hydrogens end up with some partial negative charge. So you can like consider formal charges as being kind of like a guidepost to show if the bonding pair electrons are equally shared, what are the charges of the atoms, and then let go of that assumption and think about where the electrons are really going to go. They're going to shade towards the more electronegative atom. So these electrons are all going to pull in towards the N, meaning all these H's probably end up with some relatively small partial negative, and then that negative takes away a little bit of the plus charge off the nitrogen, but still partial positive. At some point, I'd probably want to get away from talking about formal charges of every structure that we write, but it's really just the thought of the difference between formal charges. A formal charge is just assume the bonding pair electrons are perfectly shared equally, and then we can easily let go of the assumption, and they just slant towards the more electronegative atom. ICl4 minus, this compound here, would have 7 for iodine, 4 times 7 for the chlorines. We have to add 1 for the charge. So the -1 charge, I add an electron. If I had a -2 charge, I'd add 2 electrons. -3, I'd add 3. And so this gives me a total of 36 electrons. So I have central iodine, single bond the chlorines, attach my electrons to the non-central atoms. So give the non-centrals their octet. And then count electrons. That's 8 per chlorine, that's 32 total. So I have 4 electrons left to go, and there's nowhere else to put them but onto the central atom. Now what's the formal charge of chlorine? 0, right? 7 minus 7. And the formal charge of iodine is I have the 4, let me sketch this one just a little bit closer to the iodine. So the non-bonding electrons are attached to that one atom. So I have those non-bonding electrons and then half of each of those single bonds. So I have iodine's charge should have 7, but it has 8 electrons surrounding it for -1. So the charge on iodine is minus. And ICl4 minus, zeros on the outside, negative on the inside, add up to -1. So sometimes you might see a question on a test that says, like, consider the Lewis structure of a compound. What's the formal charge of the central atom? To get the formal charge of the central atom right means you properly assigned the bonding on the central atom and accounted for the non-bonding pairs of electrons the way we should, and then calculated the charge that you would get for that ion.
Does that box represent anything, or is it just like a breakup?
The box to me is breaking the bonding pair electrons in half. And so all I'm trying to do with the box is I'm trying to box an atom in. Or what I'm trying to picture is if I take iodine and I have those non-bonding pairs, and then I have half of the electrons in the single bonds. You see, it gets me 8 electrons. I'm just trying to say, what would iodine with that kind of electrons have in terms of charge? And that's how I'm just, because the idea of formal charge is really almost like removing an atom, thinking of its charge based on how many electrons it has nearest to it. Okay, so another guidepost here is if you really know all the chlorines are 0, then the iodine has to be -1 to make all the formal charges add up to -1. So if you go back to the sum of all the charges has to go to the charge of the molecule, we get that minus as well. BF3. So this BF3 will get us back into the question of what do we do with considering multiple bonds? So for BF3, 3 for boron, 3 times 7 for the fluorines, 24 electrons total. So I have my central boron, 3 fluorines, lone pairs on the fluorines, and then that's all the electrons I have available. That's all 24. So I have no electrons left over to give boron an octet. So the first thing we have to do is realize if we look at the rule that says, complete the octets, but it's of the non-central atoms. So I don't do this. Why is this wrong? Why would that be wrong? Putting those 2 electrons there would be wrong because that would be BF3 2 minus. If I had BF3 2 minus, I had 2 more electrons. That's where they'd go. But I don't have 2 more electrons, so they can't go there. And so now let's think about formal charges of this Lewis structure that we started with. And I think we'd already done this one before. But the formal charges here are all 0. Boron should have 3 electrons. Boron only has 3 valence electrons, and it has 3 electrons closest to it. So that gives it a neutral charge. If I try to make a double bond, remember the rule said consider multiple bonds to satisfy the octet of that central atom. If doing so, minimizes formal charges. If I make that double bond, if I make a double bond here, that would make my formal charge on boron it should be 3, but now it has 4, that's -1. And it makes fluorine, which was 0, should have 7, now it only has 6 for +1. That's terrible, right? This makes no sense at all. This is doing the exact opposite of what fluorine's really going to try to do. This is like saying, well, fluorine give electrons to boron so it could satisfy its octet. Fluorine's the kid on the playground who doesn't play nicely. Fluorine's not only will I not give you your octet, I'm going to take the electrons you have away from you. So what fluorine does is the exact opposite. So let me see if I can just undo all the. So let's undo all that. So if we undo, go back to the 0 charge, if we undo everything we just did, leave it as is, think about what the fluorines really do. The fluorines do the opposite. The fluorines are going to try to take this bond and pull it closer towards each of the fluorines. So boron's not going to, we're not going to increase the magnitudes of charge with a multiple bond. It just doesn't make any sense to do that. To make a multiple bond, I need a charge to pull those electrons in. I don't have that with boron. In fact, the opposite happens. The formal charges should all be negative on the fluorines, meaning they're pulling electrons away from boron. Boron goes positive. So not only does boron not go negative with the formal charge, not only does it not satisfy the octet rule, it doesn't even really have those 3 electrons all that close to it. Those 3 electrons are going to be pulled closer towards the fluorine because of how fluorine's a lot more electronegative than boron. So for BF3, doesn't we don't need to satisfy the octet rule because we just didn't end up there. And the best way to think of it is it's kind of like a balance of charge. If that balance of charge ends up satisfying the octet, then we satisfy the octet. And we see that in a lot of compounds that are stable. So we see that for almost all the other examples we looked at that were satisfying the octet rule. But BF3, this exists. You can actually buy this compound, ship it, bottle it, all that fun stuff. What about H2CO? This is formaldehyde. And so we have the central carbon, 2 hydrogens. I can single bond my oxygen. I maybe should have started with the electron count. So let me count electrons real quick. So that'll be 2 for the hydrogens, plus 4 for carbon, plus 6 for O. That's a total of 12. And so then I'm just single bonding, completing the octets of the non-central atom first, just following the basic idea of the Lewis structure. You may have already known this Lewis structure too. If you already knew it, that's fine. But if we start with this structure here, kind of just like, it's in a way similar to BF3 because I have a central atom that's deficient of an octet, but the difference here, what's the formal charge of carbon? Borons was 0. In the previous example, this carbon's formal charge is +1. How's it +1? Should have 4 electrons for neutral charge, only has 3. Oxygen should have 6, and it has 7. So that's how it's -1. So we're getting -1 for O, +1 for carbon. Electrons are negatively charged. We write them as dots, but they're really negative. What we need to, if we want to make a multiple bond, what you would want is a charge to pull the electrons in. You want this positive charge to pull this pair of electrons in to make that double bond. So we pull that electron pair in, lose it as a lone pair on oxygen, so we now only have 2 lone pairs on O, and instead have a double bond between C and O. This is perfect because what it does is it minimized the magnitudes of charge. So we took what was -1 and +1 charges, and now let's think about what these charges are once we make this multiple bond. So once we have this double bond here, the formal charge on carbon is now 4 - 4, which is 0. And then my oxygen charge is 6 - 6, which is also 0. So again, just break the bonding pair electrons in half. Carbon has 4 electrons, oxygen has 6. Perfect. They each have 0 formal charges. And then we end up with that double bonded structure. Now, think about what the electron pairs in that bond do. They're going to shade towards O because O is more electronegative. Carbon-hydrogen bonds aren't very polar. The difference of electronegativity is pretty small, so they don't really contribute much to the polarity of the molecule. So we end up with a partial negative on O, partial positive on carbon. Not quite +1 - 1. If it was, we probably would have left with that Lewis structure we had previously. But we go to a Lewis structure where we minimize formal charges, satisfy the octet rule by kind of happen chance, if you will, but by trying to satisfy the octet rule, but with the charge pulling the electron pair in, we minimize the magnitudes of charge. It was +1 - 1, 0, 0 is minimizing the magnitudes of formal charge. So think about making a -1, 0, that's a lower magnitude of charge. And so for formaldehyde, carbon, oxygen double bond, carbon, hydrogen single bonds, and then 2 lone pairs on oxygen. Okay, now there's kind of one last major effect that we have to talk about in this chapter. Let's look at nitrate and kind of see what happens with nitrate when we look at its Lewis structure, because it's going to lead to an idea we call resonance. So let's look at nitrate. So nitrate, in a way, starts off a lot like BF3 does. So for nitrate, we have 5, 3 times 6 for the O's, plus 1 for the charge. That's a total of 24. So kind of just like BF3 had 24 electrons, NO3 minus, kind of starts off with the same approach. I'm even going to kind of sketch it. It ends up looking like a trigonal plane. We'll talk about this in chapter 9 a little bit more. But I want to think a little bit about how this looks like, just to kind of get a picture of what really the real molecule might look like. So I start with my single bonds, my lone pairs, just like we've been doing. And then I account for my formal charges. So what are the formal charges on the O's? Should have 6 electrons around each of the O's, but I have 7. So that's minus all the way around on the O's. Without even calculating the formal charge on nitrogen, what should it be? It should be +2, right? Because minus 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 +2 would go to overall minus. So if you think of just the summation of charges, you get +2. You see how minus, 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 +2, overall NO3 -1. I'm just trying to show here that if you take those 3 charges and add them up, and you know this has to equal -1, you get the charge on nitrogen has to be +2. I see sometimes they're like tired, I get it. It's like Monday after spring break, we gotta talk about resonance. But we can also calculate it. Nitrogen should have 5, and it has 3 electrons surrounding it. That's a +2. So that's how we're getting the +2. Just making sure we see 2 ways of thinking of charge. The summation of charges goes to the overall charge of the molecule or ion, or just calculate it based on what the structure looks like. Okay, so now just like in the previous example, in the case of formaldehyde, we have a charge and we have a deficiency of an octet. Like we have, think of it as room for electrons and a charge to pull them in. And so we pull in a double bond. So we end up with a double bond here, and that changes the formal charge of that O down to 0. So this formal charge on this O, let me rewrite my electron pairs in here. So this formal charge ends up being 0. And then nitrogen's formal charge adjusts accordingly. Nitrogen here now has 4 electrons surrounding it. So the nitrogen ends up being 5 minus 4 for +1. So that's good too. We reduce +2 to +1. We reduce -1 to 0, reduce that magnitude to 0. And we left the other 2 as is. So this is great. Should we do it again? Should I make another double bond? What do you guys think? Should we try this again? Because I can minimize magnitude of formal charge, right? So I could go, I'm going to sketch it over here. Let me do this. Let me keep this one double. Let me keep this one single. Is this a good Lewis structure? And if not, what's bad about it? So what's good about it would be it's 0 now, right? So the nitrogen would be 0 because it has 1, 2, 3, 4, 5 electrons closest to it. And then the oxygens here are both 0. This one's minus. Why is this wrong? Remember how second row elements cannot expand their octet. So we cannot expand our octet. Even though we can minimize the formal charge, you can think, I have a charge, electrons are negative, can I pull electrons in to make another double bond? I don't have room for that. There's like nowhere to put them on nitrogen. We cannot expand the octet of a central atom in the second row of the periodic table. Kind of full stop. I almost think you should say that for all elements in the periodic table, at least in the main group. I think that's almost true for third row atoms too, but we do see that you do have some octet role violations in the Lewis structure, which I think you can support by the central atoms pulling, the non-centrals pulling the electrons back off the central atom. So the real molecules have a hard time actually expanding their octets. They find ways of selective choice of atoms that allow those compounds to form like SF6, like the fluorine's pulling electrons off sulfur. Okay, so we can't do this for nitrate beyond one single bond. So we have to stop here, even though nitrogen has a positive formal charge. But why do we choose that one bond? Like there's 2 bonds or 3 bonds that I could have chosen to make the double bond. What if I had chosen this structure here instead? What if I had chosen this double bond between that oxygen? And then the question becomes, what's the link between these structures? You know, like, if I take this electron pair, move them in here, and kick this electron pair back onto that O, I arrive at this structure. The question becomes, does the molecule do this? Does the molecule kind of kick the electrons around to this O, and does the other O say, hey, what if I get in this game too, and get involved here and make this structure over to here? So the question kind of becomes then, well, what really goes on in the real molecule? Is the real molecule, if you will, going between A, B, and C? Is it like going back and forth? The answer turns out that it doesn't go back and forth. That when we write these Lewis structures, and even when we write Lewis structures for all the other compounds we wrote, we were really trying to come up with a model. So everything we've sketched is just a picture of a model that's trying to resemble what molecules might look like in terms of their bonding. So, and when I get to this point in my model, and I see that I have what I might describe as equivalent yet different Lewis structures. So I have Lewis structures that look identical, but they're just not entirely identical. It's like there's a different bond making the double here versus here. And that the real molecule doesn't care that I can write these structures. Remember, the real molecule is what it is. These structures are just kind of me trying to understand what the molecule might be doing. The real molecule, instead of actually going from A to B to C and going back and forth here, the real molecule finds a way to be all three at the same time. So what the real molecule actually resembles is not A, not B, not C, but the average. So think about what the composite might look like. The composite would be where we have nitrogen, 3 oxygens, and then you have this extra bond at all times across those oxygen-nitrogen bonds. So the real molecule looks like an averaging of taking a single bond and then adding an extra double bond like a third of the time. So we end up taking a total of 1, 2, 3, 4 bonding pairs of electrons spread across the 3 NO bonds. That gives us like a 4/3 bond. Now let's step back for a minute. Let's step back and make sure that we picture what a single bond is. A single bond is sharing it's sharing one bonding pair, so one bonding pair is 2 electrons. So we're sharing one bonding pair across one bond. So that's a single bond is sharing one pair of electrons. A double bond is sharing 2 pairs of electrons. So I have 2 bonding pairs of electrons spread across the 1 OO bond. So that's a double bond. So we can describe like the bond type, if you will, as being single, 1, double, 2, triple, 3. So if I had nitrogen, nitrogen, triple, the bond would be 3 pairs of electrons. So 3 bonding pairs spread across the 1 bond. So that's a triple bond. So if I think about bond type, the NO bond is kind of somewhere between single and double. I would call it like a 4/3 bond. So I'd say the bond order equals 4/3, and the bond order would just be singles 1, doubles 2, triples 3. So if I'm thinking of this in the landscape of single versus double, it's somewhere in between single and double. I think we go through a couple slides before we'll get there, but you can look at single bonds are longer, double bonds are shorter, triple bonds even shorter. As you put more bonding pairs, bonds go shorter. So if we start thinking of bond length, that it's our triple bonds that are the shortest, double bonds longer, single the longest. So 1 pair of electrons longer, 2 pairs of electrons shorter, 3 pairs of electrons even shorter. So more bonding electrons, they're acting like glue, they're pulling those nuclei closer together. And so we can kind of predict that the nitrate bond length is probably going to be a little shorter than a single, but then longer than what a double bond is. So if we're thinking of nitrate, this will come up in another example where we'll try to rank some bond length trends. But we can kind of try to rank some bond length trends and kind of see how the composite structure would fit in. But the real molecule, one of the keys for nitrate is it's not one of the bonds is shorter and the other 2 are longer at any given moment. At any given moment, we get this composite structure. Let's look at a bonding model, and this comes out of chapter 9. So it is looking ahead a little bit, but this is a bonding model from chapter 9, where this structure here kind of looks like one of the structures where I have the nitrogen double bond here, the oxygens over here as single. This is the localized bonding picture of one of those resonance structures or Lewis structures we wrote for nitrate. And then the real molecule, if you notice, we have these orbitals that are all kind of pointing in the same direction. The composite structure, what it's able to do is it's able to take all those orbitals and spread those electron pairs from that one double bond, but across all of those centers at the same time. And so what this picture is how it's possible to get that resonant effect. So the resonating effect is the electron pairs resonate at all times across all 3 of those bonds. And so this is the delocalized picture of the bonding in the real molecule. So the implication is nitrate is never this, and it's always this. It's always the composite, it's always the average. And so it's never A or B or C, it's always the average of what A, B, and C would look like. So you try to composite out the average. There's a bunch of examples, like ozone does this. Ozone is O3. This is one of my silliest videos ever, was me losing it in class once from sketching this Lewis structure, because it ends up being kind of funny, but or it was the way I wrote it once. If you go back to, I think, 2018 or 19, it's so stupid. But for O3, you get 18 total electrons. And if you're coming up with the Lewis structure, you put an extra electron pair on oxygen. Let me back up a second. Don't put that electron pair there yet. Start with your 16 electrons you put on the non-central atoms. You have one electron left over, or one pair of electrons left over, that go onto the oxygen. And so then oxygen is deficient of an octet. And so you can make a double bond. So you make a double bond here, lose this electron pair here, make that 0, make this plus, and then make this one minus. And then you can resonate the electron pair over to here, and then put this electron pair back onto that O. So you end up with these two Lewis structures here. So you have Lewis structure 1, Lewis structure 2, and then you're sharing at all times whether the outer oxygens are minus or 0. But it's never like an A and B going back and forth. Like sometimes we get this confused with equilibrium. This isn't an equilibrium effect. It's not a fast effect of going back and forth. It's an at all time averaging effect that the real molecule always looks like this. And the only thing that's tricky is writing the electron pairs on these O's is kind of tricky on like where you actually sketch them. So what I'm just trying to picture here is that this pair of electrons here is just averaging itself out across those two O's. And so then how might I describe the bond in ozone? Like we said, nitrate was 4/3 bond order. What do you think this bond order might be best described as? Well, just think of how many bonding pairs of electrons we have. We have 1, 2, 3 bonding pairs of electrons. And then I'm spreading them across the 2 actual bonds, 2 OO bonds. So that's how I get a 1.5 bond order. So now if we're ranking the bonds in, say, O2, so O2's bond should be shorter than that in O3 because we have a double bond here. We have the 1.5 bond here. And then if we have the OO bond in something like hydrogen peroxide, so hydrogen peroxide would have this Lewis structure. We can maybe take a minute on that in just a second to make sure we can come up with hydrogen peroxide's Lewis structure, but this would be single. That's just a bond order of 1. And that would be longer. And the key is that the bond length comparison is like a test of whether this model is actually giving us any predictive values. So when you predict that in ozone, it's not one bond shorter, the other's longer. It's that the 2 bonds are about in the middle of double versus single. So you get 2 bonds that are each 1.5 bond order. You get the oxygen atoms charges. If you think of one being 0, the other being minus, these are about -1/2 formal charge, right? Because it was either 0 or 1, 0 or -1, so we're just averaging out the charge too. So taking the charge from structure 1, the charge from structure 2, dividing by the 2 possibilities. If we go back to nitrate for a minute, it's like, if you remember the formal charge is either minus, minus, or 0, the formal charge on nitrate, we look at the nitrate structure, look at one of the Lewis structures. So we're picturing the O is either 0 or in the other 2 possible structures, minus and minus. So the overall averaging of that structure would put each of these charges at -1 plus -1 plus 0 divided by 3 possibilities for -2/3. So all the oxygens have the same charge too. So the bonds have the same length because the bonds have the same type because they've averaged themselves out due to the resonating effect of resonance, due to the simultaneous orbital that can fit that extra bonding pair of electrons, and then the charges balance themselves out too to being equal on all the oxygens. So all the oxygens in nitrate -2/3, -1/2 in ozone. -1/2 in ozone, the central atom is plus. If we come back to -1/2 plus -1/2 plus 1, that gives us overall neutral. So you can make a lot of sense of charges too. They should still add up to the overall charge of the ion. If we come back to nitrate for a minute, the formal charge, remember how nitrate was plus in the Lewis structure because we couldn't go to 0. And so then if you take plus -2/3 for the 3 atoms, so that's -2 plus 1, overall charge of nitrate's -1. So you can still come back to a balancing of the charges. Okay, so we can rank bond lengths. In the bond length trend, I think like the single versus versus double, and then the one half bond orders in the middle. This just gives a nice comparison. If we look up bond lengths, it fits this trend. Since I just kind of threw hydrogen peroxide in. So hydrogen peroxide is H2O2. Hydrogen has to be on the outside. And then if we start with single bonds, we would have this Lewis structure here. The hydrogens can't be bridging. Like if you ever have a Lewis structure with hydrogen bridging the two things, probably made a mistake with our Lewis structure. So hydrogen has to be on the outside here. And then our total count of electrons would be 14. And then we've distributed 2, 4, 6 electrons so far. That leaves 8 electrons behind. So what if we put 4 here and 4 there? So that's one way you can come up with the hydrogen peroxide Lewis structure. Another way you can come up with it is just a dot structure approach. So if we dot structure this, we can get to it too. Or just you're kind of starting with the dot structure of O, another O, connecting them together, connecting the hydrogens together. Okay, so a few ways to get the single bond between the two O's and hydrogen peroxide. This I was going to save for chapter 9. So this slide I threw back into the chapter 9 slide. So let's save this for chapter 9. Same thing here. This is a slide actually out of chapter 9. So we'll talk about these slides when we get back into chapter 9 and this topic later. Let's look at NO2 minus real quick and then sulfate and wrap class up for today. So for nitrite ion NO2 minus 5 plus 2 times 6 plus 1 for that negative charge. Don't forget the negative charge here. And so that gives us a total of 18 electrons for 12 plus 6. And so this will probably look a lot like ozone. So nitrogen to oxygen, lone pairs on the O's. And then formal charge of, let's count our electrons at 16 electrons. 2 electrons left over onto the nitrogen atom. Nitrogen's formal charge should have 5, only has 4, so that's plus 1. And so we pull in a double bond. And so that would look like this structure here. And so then that would change the formal charge of nitrogen down to 0, because it's now 5 minus 5. And then that oxygen's 0. This oxygen's negative. And so now when we see this structure here, sometimes like how you get into the topic of resonance would be, we have to either think or consider, is there another Lewis structure we could write that's equivalent yet different? So resonance happens when we can take this electron pair here, move this electron pair back, and then sketch a second Lewis structure that's equivalent yet different. And so then I end up with a nitrogen, oxygen double bond over here, lone pair still, oxygen, lone pairs back. And so what I end up with is that resonating effect going on at all times, and it's never going to be A, it's never going to be B. We have to take the fact that we can write these structures away for a minute as being meaningful. You know, we came up with these structures based on some rules that turn out not really to apply to the case where we have equivalent yet different Lewis structures, because the real molecule will resonate. So the real molecule should look like, let me just circle one of these, where I'll take this electron pair and distribute it at all times. We have to average that bond out. So what's the average bond order? So I have the 3 pairs of electrons spread across the 2 bonds. So this is another 3 halves. And then the charge on O is either 0 or it was minus. So we got minus a half. And then the nitrogen's always 0. Now let's look at sulfur real quick with sulfate ion, SO42 minus. So 6 plus 4 times 6 plus 2 for that minus 2 charge. That gives me a total of 32 electrons. So if I single bond my oxygens, give the oxygen their octets, that'll be all 32 electrons, because that'll be 8 per O. There's 4 O's. That's all 32 electrons. So none left over for the central atom, which is good because there's really no room on the central atom for more anyways. But this Lewis structure is not too bad, because but the only issue might be the 2+ charge on sulfur. So the only issue you might have with this Lewis structure is seeing a 2+, because sulfur should have 6 electrons and it only has 4. The oxygens are all negative. That's not entirely bad, though. Oxygen's more or less a negative. It wants electrons more, so there's really nothing all that wrong with O's being negative here. But now, should we consider multiple bonds? If we did, we can do this twice. Whoop, that's too many. So if we do this Lewis structure here, is this good or is this bad? What's the deal here? Well, I've reduced the magnitudes of formal charge down to 0 for sulfur and the 2 O's with the double bonds. And then the oxygens remain negative that are still single bonded. So the charges are fine. And this is maybe okay because I've expanded the octet of sulfur. It's in the 3rd row. But I've reduced the magnitudes of formal charge. So this kind of becomes a case where the 2 Lewis structures are both maybe okay. One satisfies the octet rule, one satisfies the formal charge rule. We got to wrap this up. But the key is it would still resonate. All the bonds are the same length. Like that's something we'll start with next time is why the bonds are all the same length in sulfate, no matter which Lewis structure you look at. All right, guys, have a great day. Thanks for